Hi, folks. I thought I'd do a more well-written summary of Bayesian filtering since we went over it somewhat quickly today. And so here's a little tutorial on Bayesian filtering written out on my iPad. And I'm happy to discuss this further in office hours or elsewhere. So the Bayesian filtering problem is a problem of finding out what is P of xt given z1 to zt and u1 to ut, right? And so drawing out our graphical model of how things are working, right? So you want to say you're going to have different states, different actions, and you want to figure out what exactly the belief is at a particular time step, given the previous measurements and the previous actions, right? Okay, so that's the problem setting. Let's say we're at some, we want to figure out this entity. So let's call this belief, right? The belief at xt is defined as P of xt given z1 to zt and u1 to ut, right? And you want to figure out a recursive equation to compute this in terms of these entities, which are the motion model, right? So this is telling you how the world moves, and the measurement model if zt given xt, right? So this is motion, this is measurement, right? And so you want to figure out how to express this recursively in terms of this and this. And maybe let's say you had, a belief over what's happening at time step 0. Let's call this like belief x naught, right? This is just telling you where you are at the start of time. Okay, so the problem statement we have is we want to express this thing in terms of this thing, and this thing is the recursive equation. Starting from here is your base case. Okay, so we're going to try and break this up into 2 steps, right? We're going to break this up into prediction, and then we're going to break it up into correction, right? And so let's start with prediction, and I'll cover correction afterwards, right? So the way to get to prediction is to say, okay, I'm going to go from P of xt given z1 to zt and u1 to ut. And I'm going to, let's call this belief, right? Let's define a slightly different entity, which we'll call belief bar, right? And belief bar is nothing but P of xt given z1 to zt minus 1 and u1 to ut, right? So it's taking into account the last action, but not taking into account the last measurement, right? And so that's going to be belief bar. So belief bar is when you take an action, but not a measurement, right? And this is going to be our definition of belief bar. And let's try and first express belief bar in terms of belief xt minus 1, right? And so belief xt minus 1 is going to be P of xt minus 1 given z1 to zt minus 1 and u1 to ut minus 1, right? And so the simple rule we're going to use is this one, where you say if you have a joint probability, right? You can express the joint probability summed over B as P of A, right? You're just marginalizing, this is called marginalizing out B, and you're going to say, when you have a joint probability, you're going to sum up over B, it's going to give you P of A, right? And so what we're going to try and do is we're going to use this rule and the Markov property, which I'll describe in a second, in order to get this connection between belief bar and belief at the previous step, right? And so here's an easy way to derive that, right? So you have belief bar, which is equal to P of xt given z1 to zt minus 1, u1 to ut. Now, let's simply write this as the joint probability over xt and xt minus 1 given z1 to zt minus 1 and u1 to ut summed up over xt minus 1, right? So just pattern matching between this and this, you can see that, A is xt, B is xt minus 1. So we've just taken the joint summed up over xt minus 1, and it gives us exactly what belief bar is, right? Okay, so that's belief bar. And now we want to express this quantity somehow in terms of belief at the previous step, right? And so now we're going to use the fact that if you have P of A comma B, you can write this as P of A given B times P of B, right? This is the definition of conditional probability, right? So again, we're going to do some pattern matching. We're going to say, okay, A is xt, B is xt minus 1, right? And so doing some pattern matching, we can say that this thing is equal to sum over xt minus 1 of P of xt given z1 to zt minus 1, u1 to ut, and xt minus 1 times P of xt minus 1 given z1 to zt minus 1 and u1 to ut, right? Same as before. Now, we're going to use certain properties of our system. Well, we saw that the Markov property says that in this model, right, if you knew xt plus 1 is independent of xt minus 1, right? So which means that given xt minus 1, xt is independent of everything else in the past, right? So we can write this now as sum over xt minus 1 of P of xt given ut and xt minus 1, right? Now times P of xt minus 1 given z1 to zt minus 1 and u1 to ut. Yes? Okay. Now, if you notice, this is exactly our motion model, right? So that's great. That's our motion model. Now we have to do one small modification here. We have to note that currently it's depending on ut in the future, but you can't really depend on the future. So this is going to become P of xt minus 1 given z1 to zt minus 1 and u1 to ut minus 1, right? Okay, so this thingy gives us this, right? And now we can rewrite this whole thing as the sum over xt minus 1 of P of xt given ut xt minus 1, which is our motion model, times P of xt minus 1 given z1 to zt minus 1 and u1 to ut minus 1. Right? And now the whole point here is that this is the motion model. And actually, this is just belief at the previous time step, right? And so now you can write this as the sum over xt minus 1 of the motion model times the belief at the previous time step, right? So this is going to be your belief bar at xt. Belief bar at xt is going to be the motion model times the belief at the previous time step summed up over xt minus 1. And intuitively, this makes sense, right? So it's saying, okay, suppose this was the belief at time step t minus 1. And you're trying to find out the probability of a particular state xt here, right? So what you're going to do is take every point, right, in the previous time step, and then take the likelihood, take the likelihood that it transitions from there to your point, right? So you're going to take the likelihood that this point existed in the previous belief, multiplied by the likelihood that it transitions to your point at the current time step. And you want to sum this up over all such points, right? And that's going to give you the likelihood that you're now at this particular point xt, right? So the belief bar at xt before incorporating a measurement is just the belief at the previous step times the motion model summed up over all previous steps. Yes? Hopefully that made sense, right? And so now we've reached belief bar, but our goal is not to get belief bar, it's to get belief, right? And so let's rewrite the belief and belief bar definitions, right? So belief bar is going to be P of xt given z1 to zt minus 1, u1 to ut, right? And belief, the thing we want is P of xt given z1 to zt and u1 to ut, right? So the difference here, note, is that this and this, there's an extra zt measurement, right? And so you want to figure out how to incorporate that ZT measurement in order to make your belief more accurate so that you know where everything is. Okay. So that's where we are in the world. Let's try to figure out how to do that, right? And the key mathematical property we're going to use here is Bayes' rule, right? So Bayes' rule says P of x given y is P of y given x times P of x divided by P of y, right? And notice that you can write this also as P of y given x times P of x divided by the sum over x of P of x comma y, right? You can also write this as P of y given x times P of x divided by the sum over x of P of y given x times P of x, right? So you can almost think of take the joint, sum it over all x's, and then divide this product, right? And so the denominator is often denoted as like a normalizing constant because it doesn't really depend on x, right? You're summing out over all x's. And so this is what you often call your normalizing constant. And your normalizing constant is gonna, we're often gonna denote it as eta, right? But we'll get to that in a second. So this is the normal version of Bayes' rule. We can also think of a version of Bayes' rule with background information Z, right? So if you had some background information Z, you can now write this as P of y given x comma Z times P of x comma Z divided by P of y comma Z, right? So you've just put Z on the right side of the bar everywhere, right? Everything else is kind of the same. You've just done it with background information. All right, so this is the version of Bayes' rule we're going to use. And now to connect belief and belief bar, we're going to try and use Bayes' rule, right? So we're going to do a little bit of pattern matching. So we're going to say, okay, you have P of xt given Z1 to ZT and U1, or let's call this ZT minus 1 and ZT, and U1 to UT, right? So we'll do some pattern matching. We're going to call X xt. We're going to call Y ZT, right? And then we are going to call this whole thing the background information Z, right? And that's going to be our pattern matching into Bayes' rule, right? And so we want to be able to express this whole thing in terms of belief bar and our measurement model. So you want to say belief bar at xt and our measurement model ZT given xt. And if you can express it in terms of these, then we're good, right? So we're going to do a little bit of pattern matching. So we said, okay, we have this, this posterior function, right? Or this Bayes rule matching that we've done. We want to say, okay, we want to use the version of Bayes rule with background information. Xt is going to correspond to x, zt is going to correspond to y, and z1 to zt minus 1, comma u1 to ut is all going to correspond to the background information z, right? So now let's directly apply Bayes rule. So like we're going to say P of xt given z1 to zt minus 1, u1 to ut, comma zt, right? This is going to be what we're going to refer to as belief, right? Is going to be equal to P of y given x comma z, right? So what is our y? Our y is going to be zt given x, which is xt, and z, which is z1 to zt, u1 to u, or z1 to zt minus 1, u1 to ut, right? So this is going to directly correspond to the likelihood function here, p of y given x comma z, right? Times p of x given z. So we're going to have p of x, which is xt, given z, which is z1 to zt minus 1, and u1 to ut, right? And that is going to be our numerator, right? So we've done this term goes to here, this term goes to here, right? So we've done our numerator. And then now we need to divide it by p of y given z. So what is our y? Our y is zt, right? And what is our z? Our z is z of 1 to zt minus 1, u of 1 to u of t, right? And so what we've done here is very simple, right? We've took our belief, we've pattern matched into Bayes rule, and we've applied Bayes rule, right? So we've applied Bayes rule. You can think of this term here as p of x given y comma z. You can think of this term here as P of y given x comma z. You can think of this term here as P of x given z. You can think of this term here as P of y given z, right? So you've just pattern matched into base rules. So let me write this out cleanly so you all follow, right? So we've written P of xt given z1 to zt minus 1, u1 to ut, and zt. You can write this now as P of zt given xt and z1 to zt minus 1, u1 to ut times P of xt given z1 to zt minus 1, u1 to ut divided by P of zt given z1 to zt minus 1, u1 to ut, right? That's what we worked out from base rule. So belief, right? And we haven't identified the other quantities yet. But let's do that, right? So the first thing you want to notice is that this term right here, P of zt given xt and past observations, right, is important to connect to the Markov property, right? So we've said, okay, we have this model, we're saying that zt actually only depends on xt, nothing else. So if xt is known, it really only depends on xt, right? So what the Markov property tells us, conditional independence tells us, is that this is really equal to just P of zt given xt, right? So like this stuff doesn't matter, which is nice because this is just our sensor model, right? Our measurement model, or our measurement model. So this is great. So this is the thing we know. The the next thing you want to notice is that the second term, P of xt given z1 to zt minus 1 and u1 to ut is literally just belief bar, right? We define belief bar above. Belief bar is P of xt given z1 to zt minus 1 and u1 to ut. Right? Just pattern matching, that's literally belief bar, right? So what is the numerator? The numerator here is just P of zt given xt times belief bar, right? That's pretty cool. It became way more compact. And let's think about the denominator, right? So the denominator is, so this is the numerator. And then the denominator is P of zt given z1 to zt minus 1 given u1 to ut, right? But now, using our knowledge of conditional probability, we can write this as P of xt comma zt given z1 to zt minus 1 and u1 to ut summed up over xt, right? Same trick we did earlier. Now, you can use the definition of the joint probability here to write this as the sum up over xt of P of xt given z1 to zt minus 1, u1 to ut. So you keep the evidence the same. And you have zt on the right side of the bar times P of zt oops, sorry, I opened that the wrong way. Let me fix that. Apologies. We're gonna open the joint probability the other way. So we're gonna sum up over xt, and we're gonna say instead you have P of zt given z1 to zt minus 1, u1 to ut, and xt, right? So you're gonna say you can write it as that times P of xt given z1 to zt minus 1, u1 to ut. Right? So all we've done here is, let's think of this as P of A comma B given C, right? You can write this as P of A given B comma C times P of B given C, right? So pattern matching, ZT is equal to A, XT is equal to B, and this whole thing is equal to C, right? And yeah, that's what gives us this. And now, the same way as before, we can see that this thing, if you apply the Markov property, is just P of ZT given XT. This thing, if you look before, is just the definition of belief bar, right? And so the denominator is essentially, the denominator is essentially just the sum over XT of the motion model, or sorry, the sensor model, times the belief bar, right? And so now let's put together the numerator and the denominator, right? So the thing that you care about, which is the belief, is equal to the numerator, which is P of ZT given XT times the belief bar of XT divided by the sum over XT of P of ZT given XT times belief bar of XT, right? So you can just think of this denominator as the sum of the numerator over all values so that it becomes a normalized probability distribution, right? Because beliefs are probabilities. Great. So what does this tell us? Now we have figured out a way to connect belief to belief bar, right? And so we've said that let's consider, often you can consider eta as 1 over this sum, right? And this gives us that. And now you can write belief, right? Belief as eta times P of ZT given XT times the belief bar of XT. And so this is what you see in the slides often. You skip some steps, and the eta is just the normalization factor, which is right here, right? And so let's recap what we did from the start, right? So we started with P of X naught, our belief at X naught. We started with a motion model, right? So you have P of XT, XT minus 1 UT, motion. And we start with the sensor model, right? And now, sensor measurement model. And now what we're going to do is we're going to just apply the same process over and over, right? So you're going to have this prediction step, which we worked out above, right? And the prediction step is just going to do the following update, right? It's just going to say this update further down. So let me reproduce it down here. So it's going to say we're going to go from belief at the previous time step to get to belief bar. And the belief bar is a sum over previous time step XT minus 1 of the motion model XT given XT minus 1 UT times the belief at the previous time step. Yes, that's our prediction step. Great. And then we're going to have a correction step, right? And so our correction step is going from belief to belief bar to belief, right? So it's going to say the belief at the current time step is equal to P of ZT given XT, our sensor model, times belief bar at XT divided by the sum of P of ZT given XT times belief bar at XT summed up over all XT, right? Which is equivalent to a normalizing constant eta times P of ZT given XT times belief bar of XT, right? And so that is your correction step. So now all you do is you start from the initial thing, you apply prediction, you apply correction, and you repeat, right? Initial prediction, correction, prediction, correction, prediction, correction, and that's just Bayesian filtering, right? So hopefully that made things a little more clear. I will also be sharing, a PDF of this thing, although it's likely a little too messy to make much out of, but hopefully this kind of helps and the slides make more sense. All right, thank you all.